G'day chemistry students, in this video we are looking at how to complete calculations for titration, covering dot point 6.3.2 and 1. Let's get into it. First off, I want to have a look at neutralization in a little bit more detail. There's a simulation that I've been able to find which helps sort of to demonstrate what a solution looks like when we hit that equivalence point. We've been talking about it a fair amount, looking at how that applies to sort of our endpoint, our NPHs, and what that means for our indicators and stuff like that. But I want to give a little bit of a visual to show sort of what that means. And that might help us a little bit to inform our understanding of how to complete a calculation with the data that we've collected when doing titration. In the simulation, what I'm going to show you is that if I combine equal amounts of sodium hydroxide and hydrochloric acid, that essentially we're going to be hitting that equivalence point where there is no excess acid and base and neutralization is complete. I'm also going to be able to show using a different set of chemicals that depending on what kind of acid and base we're using, we may have different ways of reaching the equivalence point depending on stoichiometry. But let's get over there. So with this simulation, what we can do is put some acid and base particles together, show what happens to the particles when they neutralize, and in particular, get a visual for what a system looks like once we've actually hit that point of complete neutralization. So what I'm going to do first is add some hydrochloric acid particles. I'm going to put in 6. So they're all going around. I've got 6 lots of hydrochloric acid units, but then as well 6 hydrogen ions as well. I'm going to then put in a couple of hydroxides. What we should be able to see is that the hydroxides and the hydrogens interact, they neutralize each other, forming water. At this point, because we haven't added enough of the sodium hydroxide, this solution is still acidic. The pH has increased, and that's because the concentration of hydrogen ions has dropped. But in any case, while neutralization has happened, the resultant mixture at the end is still acidic, still has a low pH. If I continue to add hydroxide though, I'm going to put in 4 hydroxide particles. I might just fast forward as well to have them react. What we can see is that there are absolutely no hydroxide or hydrogen particles present at all. We just have the spectator ions, sodium and chlorine. In other words, sodium chloride solution. At this point, we've hit the point of equivalence. All acid and all base have been consumed. All we're left with is the spectator ions. In the case of titration, this would be our turning point with our indicator, going from the acidic color to the equivalence point color. If we continue to add base though, this is where we would see our third color representing the base, because at this point, what we have is an excess of hydroxide. We've added more hydroxide than we needed to be able to neutralize the acid. At this point in a titration, we have over added volume, and this would actually have an impact on our calculation if we were to take a measurement at this point in the neutralization. When we're looking at accuracy, what we're looking for is to find that point exactly like I showed before, where there is no hydrogen and no hydroxide present, or at the very least, exceptionally minimal amounts. This is going to get us the best calculation, because once we start looking at the calculations in this second part of the video, what we will see is we are making assumptions that there is no excess acid or base when we're doing our calculations. What I also want to show you as well is that stoichiometry and ratios have a part to play when undertaking some of these reactions. So I've put in sulfuric acid this time, and I'm going to neutralize with hydrochloric acid again. I've only put in 3 sulfuric acid units, so that means 3 lots of H2SO4. However, because there are 2 hydrogens in every sulfuric acid unit, there are going to be 6 hydrogens present. So if we get that going, I'm going to add just 3 sodium hydroxide. So we're adding equivalent numbers of moles of sodium hydroxide and sulfuric acid. And what we should notice is that once neutralization's occurred, there's still an excess of acid here, despite putting in equimolar amounts of acid and base. Now that is because sulfuric acid is diprotic. For every mole of sulfuric acid, there are 2 hydrogens that are going to need to be neutralized. So if I add 3 more sodium hydroxides, let them interact for a little bit, we now see that the solution has neutralized completely. And we've had to react in a 2-to-1 ratio between the sodium hydroxide and the sulfuric acid. We have a 2-to-1 ratio. And this is a concept that we are going to need to consider in our calculations. I'll just do one more. This time we're going to react nitric acid. So I've got 6 of them there should be. And I'm going to react with calcium hydroxide. If I just put 1 unit in there, still got more. Here we're reacting in a 1-to-2 ratio with the base and the acid, and that's because of the number of available hydroxides in each calcium hydroxide unit. Something to keep in mind of, it will come up in the calculations to come. Let's go do a practice question. So just to begin, I wanted to reiterate and show, I guess, chemically and mathematically what some of the things that I showed in the simulation sort of actually mean. So if I have a monoatomic acid and a hydroxide with only 1 hydroxide, these guys are going to react in a 1-to-1 ratio to produce sodium chloride and water, which means at the equivalence point when everything's being consumed, essentially there is an equal amount of hydrochloric acid and sodium hydroxide present in the conical flask at the same time. So mathematically, you can say that essentially N is equal to N. In the later examples, I showed what happened when there wasn't a 1-to-1 ratio. So in this example here, we have 1 lot of sulfuric acid reacting with 2 lots of sodium hydroxide. That is because the sulfuric acid is diatomic and there's only 1 hydroxide available for neutralization for every sodium hydroxide unit that is there. So when we look at the equivalence, we have to display it mathematically like this. Essentially, we need to double the moles of sulfuric acid to make it equivalent to the number of moles of sodium hydroxide that need to be present in solution to actually hit that equivalence point. So moving over and maybe applying that to a question. Here we have a 5 ml sample of nitric acid. We don't know its concentration. It's being put into a conical flask and being diluted to 30 mils. We then have a 1.5 molar solution of lithium hydroxide. That's going into a burette and it's being titrated against the acid. We need to use the data below to try and figure out the concentration of our acid solution. First thing that I want to do is just write up the neutralization equation so that we can make the right steps from there. So first off, HNO3, which is aqueous, plus lithium hydroxide, also aqueous, is going to react to form our salt, lithium nitrate, and the hydrogen and the hydroxide are going to react together to form water. What we should see is that these guys react in a 1-to-1 ratio. We have a monoatomic nitric acid and lithium hydroxide only has 1 hydroxide present. So 1-to-1 ratio, making the math in a couple of steps possibly a little bit easier. The next thing that I want to highlight is our results here. So what we should be able to see is that test 2, 3, and 4 have really similar volumes, whereas test 1 has a volume that's slightly different. Usually in our first test, we find that we over-add our base and end up going beyond that equivalence point. In fact, a lot of people will just treat test 1 as a way to get a rough gauge of where the equivalence point is. So they add really quickly, find that endpoint, stop the burette, take the measurement, and then go, okay, well, maybe, if my volume was 7.1 mils this time, I might get to 5 mils and add that really quickly, and then go really slow and add dropwise afterwards to try and find that point of equivalence. And then they might start taking some more accurate measurements. So when we're trying to look at our volume of lithium hydroxide and take an average of all of these tests, I'd probably just be looking at test 2, 3, and 4. Doesn't make a lot of sense to add test 1 to our average when we knew that that wasn't going to be a particularly accurate measurement to begin with. So that guy can be omitted. We're just going to be taking an average volume from 2, 3, and 4. Keeping in mind too that the unknown substance here is our analyte. The analyte is the one that we don't know the concentration of. The lithium hydroxide is our titrant. So when we're trying to find the volume of our titrant, we can just take the average of test 2, 3, and 4. So 6.5 plus 6.4 plus 6.5. I'm going to divide those values by 3. This should be equal to 6.47. Remembering that if you've got a number that's got more decimal places, carry that in your calculations. So that now, when completing a titration calculation, we want to first look at our molar ratios. So because we are reacting in a 1-to-1 ratio, we can say that the number of moles of nitric acid is equal to the number of moles of lithium hydroxide at the equivalence point. And if that's the case, we can say that the concentration of the analyte times the volume of the analyte is equal to the concentration of the titrant times the volume of the titrant. So our analyte is always our unknown substance, so we can rearrange to make that the subject. So concentration of analyte is equal to concentration of titrant times volume of titrant divided by the volume of the analyte. So we should have all of the information that is required to substitute in. Before we do that, I just want to acknowledge a couple of things. First off, the math that we've done down here is very reminiscent of the C1, V1, C2, V2 kind of concept, assuming that your number of moles of each side is equal in this case. Just to acknowledge, though, that if we weren't reacting in a 1-to-1 ratio, that could possibly change the ratios of our number of mole statements that we've done there, and then could end up having coefficients crop up in our CV statements, such as this, for example. But that's all going to depend on your molar ratios for each question. We'll practice those in class. So what we should be able to do first is look at our titrant. That's our lithium hydroxide. So we have a 1.5 molar solution, and we've determined that we can hit our equivalence point with the nitric acid of unknown concentration by adding 6.47 mils of our titrant into that solution. So that's going to be on the top 1.5 times 0.00647. That's going to be in litres. We then need to look at our volume of analyte. It's not 5 mil as is displayed here. What we know is that the solution was diluted to 30 mil. So the total volume in the flask to begin with was 30 mil. So we're going to put that in. Putting all of that into our calculator, we find that the concentration is equal to 0.324 moles per litre. But this is not the concentration of the original solution. This is a diluted concentration. So we're going to have to do a quick calculation to figure out what the original concentration was before it was diluted to 30 mils. In the flask, at all times, the number of moles of nitric acid was always equal to the number of moles of nitric acid once it was diluted. So both the sample and the diluted sample are the same. So N of sample is equal to N of diluted sample. Therefore, we can do a C1V1 equals C2V2. So just sample versus diluted is what I've got here. What we want to know is the concentration of the sample. So CD VD over VS. We know that the concentration of the diluted sample is what we've calculated already, 0.324 times the volume of the diluted solution, which is 30 mils. divided by the volume of the original sample, which is 5 mils. Putting that into our calculator, the concentration of the nitric acid sample is 1.94 moles per litre. If we're going to look at our significant figures, it seems that the best degree of accuracy that we had was 5 mils with no decimal places. So that's one significant figure. We can just round that to 2 molar, and that would be the best way to give our answer. So there we go, a titration calculation that also involved a dilution, keeping in mind that the only thing really in this question that's titration related that wasn't really a part of it was ensuring that we carry our ratios through when we get to this step here. We can do some of those in class. Thank you very much, everyone. In the next video, we're going to be looking at titration curves. These curves help to represent what's happening graphically in a titration and gives a visual to what's happening as we're adding one substance to another. But until then, have a good one.